Right, hi. So I'm very happy to introduce Andrew Godwin, telling us all about LiDAR and terrain mapping. So.
Thank you. Hello, good evening, everybody. I am Andrew. My day job is to do boring things with Python and the web, but my hobbies are far more interesting and varied and take too much time. This brought me here. So this is a talk about modeling terrain, in particular, making small different models of different parts of the world. One of my first projects was this. I apologize, by the way, this is like a weird low-res thing with a screen, but imagine it looks much prettier. But these are small metal milled national parks of the US. So I moved to America around 4 years ago, and one of my goals was I want to go and see every one of the national parks. There are 59 of them, and I wanted to do a thing to commemorate them. I started here. I then got a bit more ambitious. I got a 3D printer, and then of course bought a second one because you can't only just have one of them. And I ended up printing these giant city maps. Now, the one you see here is San Francisco. There's one of London too, is a picture later on. But they're about a meter long and about 30 or 40 centimeters high. And they're made up of these individual tiles. I've bought one here. Come and see me afterwards of various props I have here. And then finally, something else I've made recently is inspired by, a very famous particular album cover, taking sort of different terrains and doing laser cut versions of them. And again, you have one of those here, because you see it in person afterwards if you like. But this talk is about how to go about this kind of stuff. Like, where is the data coming from? How do you get the data? How do you process it and turn it into these real artifacts here? So let's start with the data. Geodata is an interesting thing. There's lots of different kinds. It's a big industry all in itself. The thing that we really want here is elevation data. That is how tall the terrain is. It is generally called a digital elevation model. None of these terms are accurate or precise. It's kind of a weird disagreement in the industry about them. But generally, you have what's called a digital surface model, which includes buildings and things like that. Or you have a terrain model, which it removes buildings and trees and just has a surface of the earth. People who do research on things like floodplains want the terrain model. People who do things on urban environments often want the surface model. You want to have those buildings there. When you have an elevation model, it often, in your head, looks like this. It's a sort of lovely set of information and data, but this is actually just a rendering. This has what's called hill shading. It lets you see the individual valleys and shading. Actual raw elevation data looks a bit more like this. This is the raw data for the big island of Hawaii, which is the source for that thing I just showed you here. It's not very presentable in its exact form, but it is basically just a load of data. There's an XY grid. Each individual point has an elevation. But of course, this is all well and good, and it's not very nice like that. We'll get to the nice bits later. But how do you get this? Well, with this wonderful 2000s era image, we can see that the space shuttle in February of 2000, I believe it was, did what's called the Shuttle Radar Topography Mission. And what that was is it had two radar antennas, one on the shuttle itself and one on a 60-meter cable next to the shuttle, as you see here in the picture. And they used radar to map the surface of the Earth. It flew around the Earth, projecting radar pulses down and using radar reflections to try and get the elevation data. Now, this was very successful, and it gave us a great overview of the Earth's elevation. There were some issues. It was early technology. There's issues with radar in general. Radar is pretty low resolution. It's great for large-scale, long-distance stuff, but it's not very good for fine detail. So it's fantastic for you're a space shuttle and want to see the Earth. It's not so great for I'm a self-driving car and want to see what's in front of me. It also needs quite large antennas. You see, you need that 60-meter separation on the space shuttle. It's not really practical at low level. This is why we have LiDAR. So LiDAR is like radar, but with light. It's a very inventive acronym. Basically, you send a laser beam at your target, you receive it back again, and you measure how long the radar beam took to go to your target. And then you put that laser on a thing that spins really fast, and you have a thing that can scan the world around it at fast pace. This here is a robot, but you see it on self-driving cars. Often they're on bottom of planes. And in general, what you use LiDAR for is more close-in mapping, mapping of city scale or individual terrain scale. So for example, this here is an excerpt from an aerial LiDAR survey of the San Francisco Bay Area. They took a plane, you stick a big LiDAR pod in the bottom of it, and the plane flies in strips over the place you want to map. And the LiDAR device literally scans the ground below it as you go, gets all this detailed information, and with that you can build up a really accurate model down to often 50 centimeter accuracy of the place below you. In the raw data here, you actually see the individual crossings and individual parts of streets in the data, and this is the low resolution version. You can of course also do it not just from the air. Here at the site itself, there was a wonderful LiDAR scan done of the campsite before everyone arrived a few weeks ago. And so this is from a van which has LiDAR sensors on it and a few cameras. And it's really versatile technology. You can map things at different scales. You can literally just map one or two walls or the interior of a room as well. And the nice things about LiDAR is it's very high resolution. You can get down to centimeter or sometimes with the new stuff, even millimeter level accuracy. The devices are very compact. A standard LiDAR scanner is around this big. All the laser interferometry stuff is much smaller than radar is in general. It only works over short distances. The problem with light in general is it attenuates over long distances very quickly. But generally, you're doing it only from a maximum of a few kilometers away, even if you're flying up, and it's probably not that far. So in general, for most things apart from orbital missions, it works pretty well. And one of the nice things about LiDAR in general is that even though it's very expensive to do, a lot of free data is available from different governmental departments. In particular, our very own Environmental Agency and other parts of the UK government have free data available. The Environment Agency have basically mapped most of the floodplains and coastal areas in the UK with free LiDAR, and I believe there's an ongoing project to map a lot of the rest of the country in LiDAR for free as well. And over in the US Geological Survey have mapped most of America in a sort of low resolution, and again, a lot of floodplains and coastal areas in high resolution. LiDAR is often used for floodplain and modeling and analysis. That's where you see it often more near cities and rivers and things. So we have this data, we have a basic idea where it comes from, but what do we do with it? Well, the problem with LiDAR is it's not a nice, simple elevation model like I showed you earlier. What you get back from LiDAR is a thing called a point cloud. Now, a point cloud is literally a load of points individually in space with no link to each other. You might get what color they are, you might get what sort of intensity the laser bounce off of them, but there's no link. If you zoom in, you just go through this swarm of points. There's no solidity to them at all. You can't work out what the surface is. And so we have to take this point cloud and turn it into something we can actually use. If we feed this to a 3D printer or milling machine, it's not going to do anything. It's just literally a point. These are dimensionless points in space. They have no material being. And so that's one of the problems. But the other problem is it's also not pure data. LiDAR, when you get it back, there's a couple of things extra. When the laser hits something, it might hit more than one thing. You get what's called multiple returns. And so you may, in fact, get in any given point a series of diminishing points behind each other. If you're flying over something, you in fact may get several different features below you in the same vertical space. If you're trying to make an elevation map, you might get, well, there's a top of a building, but also we went through the glass to the floor below it and got like a weak return from that. Or we can see through trees and things like that too. And in general, it's just quite noisy. The data tends to be marred by reflections. Water and steel is especially bad. Also, if you go anywhere near like a power plant or something hot, one of my favorite examples recently is I was looking at a bit of Didcot, and Didcot's pretty well mapped, apart from over the power plant, there's a sort of giant mess as it sort of starts going near all the giant steam emissions. There's a quick example here. This is the sea off of, I think this is San Francisco again. There's just random spikes in the middle of the sea. I can reassure you, there are no random spikes in the Pacific Ocean. I've checked myself. But the LiDAR occasionally bounces a wave and thinks there's a spike there. So you have to sort of get rid of that stuff. And in general, we have to do more than that. We have to take our point cloud, we have to thin it. We have to take the point cloud and go, well, there's individual data here to much higher accuracy than we need. I'm not printing a tree in this kind of size, I'm printing a much sort of zoomed out model. And so we have to take all those points and reduce the resolution. Often what I'll do is if I'm doing a surface model, I'll say, okay, for each small like 10 centimeter grid, find the highest point and just give me that. And that way you can thin it out to a nice grid. You then have to take those points and turn them into an elevation model. Often this is easy as looking in that grid square, taking the highest point and just writing it into a file. These two first steps can be done with a variety of pieces of software. Unfortunately, none of them are entirely free. I use what's called LAS tools, which is free for small amounts of data and evaluation use, but if you're to use it commercially, you're going to pay a licensing fee. If you're lucky and your department is good, and this includes the UK government who are good at this, they will just ship you ready-made DEMs from the LiDAR data, so you can skip the first two steps. You can also have to smooth the results. This is done with, in my case, some special code that just sort of tries to average out the different stuff, but you have different techniques here. You can try clipping, you can try reducing stuff. And one problem I had was when I got data back from a LiDAR scan of London, it was when Crossrail was being dug initially, about 2014 or so. And the data was like, oh, there's loads of points that are like minus 40 meters below sea level. And of course, it had seen the giant pit they'd put the TBMs in. And so I had to, rather than print a model that had this thing with a big hole in it, I had to tell it to like smooth it and bring it up to sea level. Like nothing should be below sea level. We'll ignore the giant hole in the ground for now. So that's kind of the easy part. Taking the data, getting the data, there's well-known places to do this. And it's not easy, I'm being a little bit overzealous here. But we have GIS tools, we have ways to do this, it's tutorials online. If you want to find elevation data for a part of the world, you're at least going to have a rough resolution of data. You might get mountain level rather than city level. But then we come to fabrication. Now, one of the things I was maybe a little bit too, shall we say, overzealous about initially was, oh, it'd be really easy to make these. How hard can it be? Well, let's go through the three basic techniques I've been using here. 3D printing, which is what makes the city models, things like these tiles here. Laser cutting, which is what makes those sort of wave-like shapes, like this one here. And then milling, which is what makes the small metallic shapes as well. So let's start with 3D printing. 3D printing is, thankfully these days, pretty cheap, very really, like quite accessible for a lot of people, and quite easy to get stuff into. The basic requirement is you have a 3D model. That's kind of it. Once you've got a good 3D model, the slicer will take care of the rest and give you a good tool path and let your printer do most of the work for you. So the basic thing here is to take that data and turn it into a 3D model. This was achieved, in my case, through a wonderful Python script. It is open source, links at the end if you're interested. But this takes the data and makes it into 15 by 15 centimeter models as STL files. Now, this data is quite detailed. It tends to be on the order of 25 to 50 megabytes per tile. Some 3D printers do not like this and will just sit there and complain for about 10 minutes and then fail. So there's options for making it less and less detailed so it sort of fits in the printer. But in my case, I took these big tiles, I put them on one of my 3D printers at home. This is a Cetus Mark III, and left it to print. So 3D printers, thankfully, are unattended. They're fully automated. Now, the problem is this is a very detailed model. It's got a lot of fine detail and like tiny buildings. It's got to like print a little bit, lift the print head, travel over, print a little bit again, and keep doing that. This means the tile of this size, which is about this big, is between 4 and 12 hours of continuous printing. You've got to sort of put it on and then just go to bed, wake up in the morning, and hope you don't find a big spaghetti mess of plastic in the morning, which unfortunately has happened sometimes. And then the problem is you're printing tiles. You've got to assemble those tiles into a bigger whole. Now, ideally, that looks like this, but this is after hours and hours of meticulous work, sanding the size of the tiles down, making sure they're perfectly square, aligning them and trying to glue them perfectly. And in the end, it works out pretty well. If you look very closely, you can see the seams between the different tiles. My 3D printer's not exactly making perfectly straight edges, but it generally works quite well. And again, here's the London one. This is a bit more like East Endersy. You can sort of zoom in with your head if you like and sing the theme tune. If you look closely here, maybe put it on this projector, you can see visible seam lines in this one. These tiles aren't as good. In this case, my printer was not behaving perfectly right, and so I had to do a second pass of these and sand them down to be perfectly square. And so it's a relatively easy method. What I like is it's mostly unattended. You run the script, it makes a file, you press print, and then you just go and do something else for 12 hours. There is a little bit of manual work involved, that sort of lining up portion and making sure it's all correct. And the gluing stage is a bit tense because, like, well, once the glue's on, you've got 20 seconds or so of work time before it sets. And if you get it wrong, you've got to peel it off and hope it looks all right again. So it's a good start. It's not particularly durable. The ones you've seen here are printed using PLA. If you know 3D printing, you'll know that's a cheap but not relatively durable plastic. I want to move up to ABS and other things too. There's a variety of plastics you can 3D print with. But in general, 3D printed stuff is a little bit brittle and it's a little bit hard to deal with. So let's move on to something that's much more durable, which is milling. So if you're not familiar, milling is sort of the opposite of 3D printing. 3D printing is additive. You start with nothing, and then it adds plastic to build the model up. Milling is different. It's subtractive. You start with a big block of metal, in my case, aluminium, because aluminium is cheap and easy to work with. And then you have a mill which progressively carves out the shape with multiple passes. In sort of a similar way you build up layers in 3D printer, you carve out layers with a mill, smaller and smaller and smaller to build out a shape. Here you can see it's about halfway down a copy of Mount Shasta in California. Now there's a couple of problems with milling. First and foremost is you've got a certain shape of milling bit. Often it's circular. You can have a flat end or a round end. This one here is a round-ended one. But if you want to do small detail, you need a small bit. In fact, you need to be very, very small. But the smaller it is, the slower it goes. And so you want to do a big rough pass with your big, nice big milling bit first, and then a sort of medium pass with a half-size one, and then a final pass with a small-size one. And in between these, you've got to have the machine come up and let you take the bit out and put the new one in and know the depth properly, and it's a lot of manual work. Whereas 3D printing is unattended, milling is not. It's kind of unattended. You can kind of sit there while it does each pass. It's about an hour or so per pass. But between those, you're going to get up, change the tool out, and do all that kind of stuff. There are machines that have automated tool changing. I would probably give some sort of limb to have access to one, but they're very expensive. And so the one in my local makerspace in Oakland in California does not have any of that. It's very much you get to put new bits in and do it all manually kind of machine. But the nice thing is the final result looks really good. You get these sort of very small detailed models, almost intricate in their design, of various different national parks. And things like the mountains and the terrain come out really well. These are the 6 I've made so far. Given how long they are to make, it requires me to have an entire free evening, just go and sit next to the machine and just listen to a podcast while it whirs away and hope it doesn't break anything. I have broken about 10 milling bits at least making these 6 of them, because as you go smaller and smaller, they break really easily. So I'd be carving out a valley and go boop, and just break off. The other problem with milling is it's not quite as simple to just feed a model into the machine. You have to take the 3D model, feed it into a CNC program. I use Fusion from Autodesk, and then sit there and manually tweak the tool paths and tell it the strategies to use. You say, oh, I want you to do this kind of flat pass first, and then a pass with this milling bit. And there's a good 30 minutes or so each one of these of me sitting down and planning out how the machine's going to work. Most of the routing is done for you, but the strategy, the high-level idea is yours. And you sit there and go, well, can I shave half an hour off the time by changing the strategy a little bit? So it's a lot more involved in general, which is why they're going a little bit slower. They are a bit faster than 3D printed ones because they're a lot smaller, obviously. If you were going to mill a 1 meter thing, it would take almost forever, I imagine, on the machines I have access to, and it is attended work. You can't leave a CNC mill alone. They're giant spinning wheels of death. They're kind of dangerous to get near. So you want to make sure they're attended, not going to sort of like ram themselves straight into the side of the piece and just spray aluminium everywhere. The small features also are hard to mill. I have an example in my bag. You can come and see it later if you want. And it shows very well, like there's a little bit between two mountains that it just couldn't get to. There wasn't a bit small enough to mill that part out. So you lose a bit of features in those deep valleys, which is a problem for anything with mountains in it. And finally, CNC mills are one of the most expensive things I'm going to refer to in this presentation. The entry-level model is like £10,000. And also, you have to have some light industrial space to put it in. And also, you have to have like some air extraction in that space. And also, you then need all the tools as well. I would love to have one. I do not have the money or the space to do so. And so, thankfully, makerspaces kind of solve this problem. But even then, a lot of makerspaces don't have the budget or the expertise to run a CNC mill as well. It's kind of rare by itself. So that's often kind of the big blocker to doing this as a project. I really hope in the next few years we get more of a revolution in desktop or smaller CNC mills. There's a few of them out now, but we could make a lot bigger steps in having smaller, more accessible milling for this kind of stuff. But finally, everyone's favorite, laser cutting. I think pretty much every makerspace from here to Sydney has a laser cutter. They're incredibly popular and incredibly easy to use. I love the things. That's one of the reasons I then took to the laser cutter for this third project, because it's something that I can literally just plan out an SVG file, send it to the laser. It's about 15 minutes to cut all the pieces out and then a little bit of gluing. This here is an example of one of those sort of profiles that's being cut by the laser. I have a piece of software that simply takes the terrain data you want, you slice lines out of it in 2 dimensions, and then for each of those lines, you take the sample of heights and turn them into a side-on view as a solid object. That ends you up with about 30 or 40 of those individual pieces. Obviously, I would cut a giant piece of plastic. This is an illustration of one of them. And you get this big piece of plastic, you pop all the pieces out, you glue them on to a nice little ridged bed, and you end up with stuff like this. This is my first attempt. This is the wonderful Scotland. It's not great. I used clear acrylic. I didn't realize that because it's clear you can't see it. It's kind of an obvious thing. It looks lovely when you shine a light from the back of it, but unfortunately it's very hard to photograph. Another problem is Scotland is almost too big. When you're zoomed out that far, the height of the mountains is not that high relative to the height, the size of the landmass. And so I tried to exaggerate the height and like say, oh, make the mountains way higher, but it doesn't quite look right. I'm still working on this. I want a nice Scotland on the wall, but that's taking a bit of work. What is easy is Hawaii, because it's giant and surrounded by sea. So various islands of Hawaii you can do this to pretty easily, because they are very, very high, like 10 to 12,000 feet each. You can drive from sea level to 10,000 feet in an hour. It's ridiculous. And also, they're quite small. They're only about 10, 15 miles on each side. And so you get that nice ratio of height to depth. I also think things like the South Island of New Zealand could be good for this. There's a few other options as well. There are a few problems with this, though. The sort of presentation of this has a few flaws. First of all, you can't see it if you're looking straight at it, because it has to be viewed from the side, which actually means you want to do them side on so you can see them as you walk around the room. If you do them vertically, then people of a certain height will never see the artwork. If you're short or tall, it's great. But if you're like, exactly an average height, you're like, why is there just a random grid on the wall? It doesn't make no sense. Other problems is I tried it with things that were sort of cut out portions of landscapes, but it kind of needs things that are surrounded by flat edges. Islands, obviously, perfect for this. But also, if you've got sort of a big mountain in the middle of a nice flat area, there's a few of those around the world, that would work pretty well. And of course, it's limited detail. This is much more of an artistic interpretation piece than most other ones. It's very much going to show you the rough outline of how it looks. It's not really going to show you fine detail, and the script takes a lot of liberties in exaggerating peaks. In fact, it multiplies everything to a power of 2 to really push up the mountains and bring down the valleys to make you see those details much more clearly. That's kind of the secret of all of these. Everything I've showed you, the London model, all the city models, everything has the height exaggerated Because if you just look at a normal scale model, you're like, oh, yeah, that's really flat, it's boring. You have to have that exaggeration to make it seem interesting, to have it see how you see it when you look out the window of an airplane, for example. So that's a brief rundown of the stuff. There's a few things next I want to work on. These projects are all kind of in progress, along with my other like 3,000 hobbies. They all get like time shared. But one of the key things is I want to do more milling. There are 53 national parks remaining. I do not have 53 spare evenings in the near future. And so I need to work out a way to do a less human-intensive version of that, whether it's doing them quicker or whether it's somehow finding a milling machine with an automatic tool changer and like bargaining with someone for that, or sending away for it even, I'm not sure. For laser cutting, I want to work on the feature highlighting. As I said, getting Scotland working would be great. It's a case of working out how do you make a nice defined coastline, but still bring the mountains up to be really obvious. I want to see the Great Glen in perfect detail while still seeing the shape of the landmass. And that can be really hard to do when the edges can be quite flat compared to the mountains around it. With point clouds and LiDAR, one of the big things we'll do there is 3D directly from the point cloud. What I've shown you here is taking the point cloud, making it into like a 2D height map, and then making that into a model. But what that means is you lose undercuts. You lose like buildings that have things underneath them. And in London, like the Gherkin would render as just the top half and straight sides. And so you need to do a bit more for that. There's some commercial solutions, but I'm a cheapskate. And so trying to find a way to make a script that actually parses point clouds directly into surfaces is my next interest. And then maybe I can get a LiDAR scanner. When I said the CNC mill was the second most expensive thing, LiDAR scanners are the most expensive thing. The entry models are like £20,000. I do not have that anywhere. There are handheld ones, but it's one of those things like I'm hoping like as we get them and like they're used like as a crucial component of self-driving cars, they come down in price a bit. If you're curious about more of this, some of the code to make 3D models is up on my GitHub. There's a few blog articles with some of the process of this as well. And there is a couple of videos of me making the process and going through the big city models on my YouTube channel as well. It's about 20 minutes of me mostly faffing around gluing things badly. Please don't hate me for my bad at gluing. And that's basically it. Thank you very much. Yes, we can do questions. We have the giant throwing box of questioning. There's a hand up over here. Whee!
So do I just, I guess I just talk in the box then?
Yes, to hold it very close and talk loudly.
That's awesome. Thank you very much for the talk. It was really good, actually. I had a question about actually more of an idea. I really like the idea of laser cutting the edges and then stacking them. That's really cool.
Yeah.
And I also understand you've got a problem for kind of looking directly at it. You wouldn't be able to see, right? So what about maybe building your model and then putting it into a vacuum former? So this way it would actually fill, put a very thin sheet of plastic between all of your layers basically, and kind of fill it. So this way you'd have like a completely filled model with shapes. So wherever you look at it, you'll still get light refracting from it, and it would really pop, I think.
Yeah, that's a good idea, actually. Another one, same thing is, I've also tried casting those shapes into, and like to get a negative of them, basically. That's another way of doing that too.
Okay.
But yeah, like there's a lot of interpretations of that. Like this is only a few weeks old, the laser cutting, so like it's the most recent thing, it's the least developed, I'd say. Right. But yeah, that's a good idea, I think.
Because I think you could potentially just stick it in and just press it down, and that might work.
Yeah, it's the wonder of vacuum form. You just pull the lever and it works.
Yeah, exactly. Maybe another thing is expanding foam. Do you think that would work?
I haven't got any of that around. It's kind of
messy. Really
it's
cheap,
kind of
though.
messy, though.
That's right. You need to do a lot of cutting.
Yeah. But yeah, these are good ideas. Thank you.
Thank you very much.
Yeah. Any more? Oh, over there. Do you want to throw it over there? Whee! Oh, too much.
Hello? Is it still working? Yeah, it's working.
Yeah.
Have you seen the Polish map of Scotland?
The what, sorry?
Okay, so
No is the answer, but yes.
so about an hour south of Edinburgh, near Peebles, there is what claims to be the world's largest terrain relief map.
Ooh.
Called the Polish map of Scotland or Map of Scotland, and it's made of concrete and it's 10x vertically, like exaggerated basically, but it's probably as big as this tent, if not bigger. It's next to a like a country home, but it's really cool.
That sounds amazing.
Go see it.
Okay, that's going on my list of things to go see. Thank you very much. Over here. One more?
Yep.
One more question, okay.
It was just about your milling.
Yes.
Whether you've considered milling perhaps wax or much softer materials, which you could potentially then lost wax cast or something like that.
Yeah, I think in terms of increasing the speed, I was looking at literally milling, machining wax, casting that, and then casting it into a resin. The problem is I quite like having aluminium as the result, and I don't really have the ability to, forge or cast metals. And so it definitely would be a way of increasing speed and making like nice resin versions. I'm not sure I can get the same like aluminium like machine effect out of it.
Is it specifically aluminium, or are you just wanting a harder metal?
Well, I mean, the softer the metal, the faster it is, right? Yeah. Bronze or aluminium is quicker. Like you can mill iron, I guess. But
bronze is something you could sort of potentially cast.
Yeah. Like I haven't done the milling for a couple of months now. I lost access to the machine a while ago and just got back access to a different machine. So I need to start on that new machine basically.
Thank you.
Cool. Oh, was one more question in the back? Oh no, come on, let's go. Up. Go long. Right. There we go. Okay, yeah, there we go. Away from people, even better. Hey.
And the scan that you did of this site,
yes,
that looked like it was done optically rather than LiDAR, as in, was that a camera image?
So it's not my scan.
Yeah.
It's somebody else's scan. I've blanked on the name temporarily. Yes.
I've done some work using Open Drone Map, and it looked very similar to that. And one of the advantages of that, you could just take video or photo images and it stitches them.
Right.
And I wondered if that was done the same way.
No, so that scan was done using a professional LiDAR van with a laser rangefinder, I believe. You can do what's called photogrammetry, which is what you're talking about, where you take lots of pictures and then you use the just differences in the pictures to work out the shape of the terrain. That's much cheaper because you just need a camera, basically. It's also much less accurate, and doing the stitching into 3D models takes forever. I have some photogrammetry of, I think, Crater Lake in Oregon, and it took like 3 hours to render the model out of it. So it's possible, but it's difficult.
Indeed, I did a scan of our local hackspace, and that was a 12-hour render.
Right, exactly. So like in terms of like throughput and accuracy, like LiDAR is the thing and also it's being improved a lot too. But then also maybe photogrammetry is as well.
Thank you.
Cool, thank you. I'm not sure on the question. No? Okay. Yeah. Yes. The person with the scan is right here. He's amazing. Please ask him questions. All right.
Actually, I've got.
Oh, you got a question? Okay. Oh, sure. Go for it.
So, actually, could you make your own LiDAR with like an old laser printer or something like that mechanism? For less than 20 grand or something?
The laser is not the hard part. It's the receiving of the laser that's the hard part. Shining laser is very easy. Accurately measuring the time of flight, much harder. There is decent entry-level like single laser stuff. It's the case of like taking that, mounting on an accurate gimbal and mapping it and stuff like that, basically. But yeah, I'm probably going to get like the most basic laser rangefinder I can try, and like try to do a sort of cheap, hacky version of it. I think is my next project.
Cool. Okay.
All right, thank you very much.
Well, thank you very much indeed for your talk.